integral. It's only going to work when there's an integral number as the answer. But I found a whole bunch of those, and then a whole bunch of the few theorems that show how you can relate one to the other.
Could I just, sorry to interrupt you, Ken.
Yeah, ask.
No, I was going to ask Lou, are you recording this?
I hope not.
No, I'm not recording.
To...
I thought you were recording.
I've just remembered I forgot to set the recording.
Or you could start now.
Yeah. This is kind of a talking exhibit.
I'm very sorry, Ken. I just forgot.
That's all right. I'm trying to move this thing on the screen, and I can't seem to do anything to affect it. But
what is it that you want?
I'd like to scroll up a little bit on what I'm looking at.
Is that better?
That's it. Yeah, that's better. I'm getting a blockage. Yeah, that's fine. I'm getting all kinds of things. I hope I'm not messing the meeting up. Rolfson's. The other interesting thing about doing this kind of a construction to find a co-bounding surface for the branch of index 2 is that it doesn't necessarily survive Reidemeister moves, which means that it can work for some diagrams of a knot and not work for other diagrams of a knot, which is kind of an unusual situation, if I'm not wrong, Lou, right?
Well, you're saying finding these good cells is easier in some diagrams than some representations.
It's possible in some, but then if you make a Reidemeister move on the diagram, it's impossible.
Right. The linking number the linking number remains the same, but the
ranking number remains the same, and the surface goes somewhere. But the nice thing about constructing the surface this way is it's sort of flattened out like pancakes, the way a canonical Seifert surface is, so you can see it. You know, there are plenty of other Seifert surfaces of a knot diagram, but they sort of wrap themselves all around in strange ways, and who can see them? I mean, I'd love to be able to see the minimal Seifert surfaces for those two knots, the Conway's knot and the Kinoshita-Terasaka knot, but I have absolutely no idea what they look like. I suspect they're not the canonical Seifert surfaces, but the nice thing is
that because the Seifert disks are nested, maybe.
Yeah, but
if we're just looking for Seifert disks, never mind the covering space, then many diagrams have nested Seifert circuits. But every knot does have diagrams that have no nesting.
Yeah.
Yeah. So diagrams can make a real difference. It's like looking at the knot from a different perspective, and that gets compounded when you construct the covering space because you're looking at the covering space from a different perspective. So things that are nicely visible because they're flattened out like a pancake in one diagram, you just can't do that in a different diagram. Anyway, another example I really like is Rolfson's knot 1087, which, bear in mind, I'm working with 3-colored knots, and 3 colorings aren't all that easy to find. If you have a 3-bridge knot, you got to test 4 different cases, and maybe 1 will work, maybe all 4 will work, but you don't really know. But what I like about 1087 and a whole other series of examples is it's weakly 2-bridged, which means you can find 2 segments, which I've labeled on the left 1 and 2. And if you label them 1 and 2, or any 2 different of the 3 colors, you can fill in the rest, because you're not just doing it Wertinger's way at crossings. You're also using the 2 end crossings to label a middle one. So that any diagram, and there are plenty of them, at least in the lower crossing number tables, any diagram that's weakly 2-bridged, it's easy to find its 3 coloring. Well, it's as easy as finding 2 segments that generate the whole rest of it. Now, the other thing I like about this particular knot is you can make the threefold covering space the way that it's done at the top there by matching the two missing colors under each one. But then you can construct two entirely different surfaces that are bounded by the index 2 branch. And for the one on the left, for example, you start with the upper left-hand crossing, and you can lift the top of it to copy 3 and the bottom to copy 2. And then if you extend that around, you can see that works to fill in the rest of the ciphered, so-called ciphered surfaces, ciphered circles, in a consistent way that shows the linking number to be 0. But you can also, starting at that same crossing, instead of putting the top in copy 3, you can put it in copy 2 and the bottom in copy 3. And then if you wander around, it turns out you can get another one of these surfaces, which also bounds the index 2 branch. But they're quite different because, among other things, they have different genus. Now, Fox pointed out in his trip through knot theory how you calculate the genus of a canonical ciphered surface. It's half of one more than the number of crossings minus the number of ciphered circles, nested or not. That's always the genus of a canonical ciphered surface. And that formula works here for these surfaces as well, because basically they've been flattened out like pancakes. So if you ignore the thing they're embedded in and just look at the surface, you basically get a ciphered surface. So the same rule applies. The genus of each of these surfaces is half of one more the number of smooth crossings where a little twist is put in, minus the number of capping discs that go around the ciphered circles. So these are two different surfaces that co-bound the same thing, but they're intrinsically different because, among other things, they have different ciphered genus. Now, some of what I've done in this little short paper that should be coming out shortly is if you have a knot like this and a surface like this with this one of these constructed surfaces in pancake form, you can take any monochromatic crossing and reverse it, and you're still going to be bounding one of the covering branches, but you're not going to change the intersection number. So if you have a three-color diagram with one of these surfaces, you can reverse any one or more of any monochromatic crossing, and you'll get a different knot or link, but with the same linking number between branch curves. And then it turns out that you can also play with you can either reverse it or you can eliminate it, just smooth it away. Sometimes that turns your knot into a link, or you can multiply it, but none of that has any effect on the intersections. Now, the other nice thing about surfaces constructed like this is it's a little hard to see where the surface is intersected by the branch curve of index 1, but it turns out that it's always over the unsmooth crossings, the ones without the little twists. So you can just sum the signs of the unsmooth crossings, which is 0, and it's 0 for both because it doesn't matter how you bound one of the curves. And then the other thing is there are some theorems I show for manipulating tricolored crossings. You can take a tricolored crossing and you can replace it by a reverse double crossing. That will preserve the tricoloring. And if you do that, that changes the linking number of the branches by a factor by 2. 2 times the sign of the crossing you reverse. So that if I start with some diagram, any diagram with one of these nice nicely laid out surfaces that bounds the index 2 branch, I can manipulate right and left and generate a whole bunch of other diagrams with similar surfaces and predictable changes in all the linking numbers. Lou, do you have those 2 other things that I have? One is called, I think, Scan 20. Ah, yeah. This is one. These are all the examples of 3-color diagrams that I can find that have these nice little surfaces for 2-bridge and weakly 2-bridge knots. And it turns out that the table diagrams in the standard tables work very nicely for all of them. And it's a good hunk of what I did on a computer in my thesis, for which I didn't need a computer. The top ones are all the 2-bridge knots. The bottom ones are all the weakly 2-bridge knots. Sometimes it's a little hard to find 2 segments on a weakly 2-bridge knot that generate the whole diagram, but there aren't that many possibilities, and ultimately you can do it. That way it's easy to find the 3 coloring. And then when you find the 3 coloring, you can, all of these examples have a nice Seifert-like surface in the cover that, yep.
Yeah, 7-4 is 2-bridge and 3-colorable, and I don't see it in this table.
That's because it doesn't have one of these nice surfaces.
Okay.
What did you say, 7-4 or 7-7? There are 2 of them.
I think 7-4.
Yeah, 7-4. 7-4 does not have one of these nice surfaces in its standard 7-crossing diagram. Now, I conjectured in this paper that's coming out, and it's more of a wild guess than a conjecture, that it does have some diagram with such a nice with a nice surface visible on the diagram. Some diagram that could have a hell of a lot more crossings. For example, every 2-bridge knot has a dihedral covering based on with a number of sheets in its determinant. But the Schubert's so-called normal form diagram of a 2-bridge knot, which really gets out of hand fast. You get an enormous number of crossings for a very small crossing knot. But that particular diagram also produces a model for the covering space where you can see the linking number, sort of in an opposite way. You can see a surface that is bounded by the index 1 branch. This I mentioned in my my paper on dihedral covering spaces of knots, which was in Invenciones in 1974. And I'm not sure anybody has actually gone through the exercise of seeing how you can see these linking numbers. But the only way to see it on a knot like 7-4 is to go into the hugely multiply crossing diagram that Schubert has as his normal form diagram. That reveals a nice surface that is bounded by the index 1 branch. And then Lou, there's one more of these.
Yeah.
Mm-hmm. I like the knots more than I like the knot theory, so I just love compiling tables of these things where you.
I have the other one up now.
Yeah.
Starts at 9. It starts at 940, right?
Yeah. These are the all the primes through 11 crossings that admit these nice surfaces and have just one 3 coloring, but are not 2-bridged or weakly 2-bridged. And because they're not 2-bridged or weakly 2-bridged, it's kind of hard to find a 3 coloring. So what I've done here is I've darkened the segments that carry the same color. So you for example, for the knot, what is it, 1140, halfway down the page on the right. If you color all those darkened segments 1, and then throw a 2 in for another one and work the rest out, you'll get the unique 3 coloring, which otherwise is kind of hard to find.
It is in N85.
What?
In the knot N85.
N85.
Is there an arc missing down the bottom?
Oh,
bottom right.
N185.
No, N8.
N85. A third line from the bottom.
Yeah.
Oh, third line from the bottom, second from the end.
Yeah.
Mm-hmm.
Is that fading? What's going on?
I can't see.
I think it's got a couple of little spots that we should ignore.
All right. Okay.
It's pretty small on mine, but
N85
looks good to me. It's yeah. Where are the spots?
Well, the bottom right.
There's a segment is missing.
Right.
Yeah, there's a segment missing on the outside.
Yeah.
Oh yeah.
See, right there. Yeah, that's got to be joined.
Yeah.
You're right. Yeah.
Yeah.
But once again, you can take a diagram like this that has a visualizable surface bounding the index 2 branch and manipulate it in all kinds of different ways to get predictable linking numbers for the result that you get. Going back to that the slide before this, Lou. These are the 2-bridged examples at the top and the weakly 2-bridged examples at the bottom. The 2-bridged examples, the 3-fold branch cyclic covering is always simply connected. For the weakly 2-bridged one, Capell and Shanison proved a long time ago that the branched 3-fold cyclic covering is always not a Z2 homology sphere, which means it has Z2 homology. And one of the papers I wrote a long time ago shows that every homomorphism of a knot group on the symmetric group on 3 letters can be extended to a homomorphism under the symmetric group on 4 letters. And I did that in a very roundabout way by lifting the 3-fold representation to a 4-fold representation, and there's a little lemma that says you can do that if and only if there's 2 torsion in the homology of the 3-fold branch cover. So all of these knots on the bottom of the page, which correspond to weakly 2-bridge knots, because their covering spaces are not Z2 homology spheres, they can all be lifted to these 4-fold simple covering spaces, where you've got 4 different copies of the 3-sphere joined together, but just a little just joined by a transposition on each. So you get three different branches in the covering space.
Yeah.
And there are similar rules for manipulating, reversing crossings and changing crossings and adding and subtracting crossings and still being able to predict a linking number for those 4-fold simple covers. Yes?
Yeah, I'm confused. If I have a 2-bridge knot and I'm looking at a 3-fold branch cover of S3 over the 2-bridge knot,
yes,
I can construct, excuse me, I can construct that by starting out with three balls and then adding 2 1-handles between them at the bridges.
Say again?
So I can construct it by starting out with 3 balls.
Yep.
And then add 2 1-handles between them. And the boundary of that is a sphere, as long as I use 2 colors on the bridges. And so it looks to me like the three-fold branch cover of a two-bridge knot is always a three-sphere.
Yes, it is.
Okay, so you were saying something about homology spheres, and I guess I missed.
I was talking about the weakly two bridge knots.
So
The
what do you
weakly
mean?
two bridge knot, it's never a three sphere because it always has Z2 homology.
So what do you mean by weakly two-bridge?
Weakly two bridge means you can pick two segments and generate the whole diagram, where you don't just take an undercrossing through an overcrossing to generate the other undercrossing. You let two undercrossings at a crossing generate the overcrossing. That's weakly two bridged. It hasn't been studied much, but Shanison and Capel did some work on it back in the 80s.
Okay.
And it turns out the weakly two bridge knots all have Z2 torsion in their threefold branch covering.
Okay.
That's sort of it gets kicked off when you come to the first crossing that has to be generated by using two undercrossings to generate an overcrossing. That introduces some Z2 homology into the threefold cover, and that just never goes away. So all of these knots on the bottom of the page have Z2 homology in the threefold cover, and therefore they have a nice simple fourfold cover.
Okay.
And for the fourfold covers, just as for the threefold ones, you can construct these surfaces that bound branch curves just about almost all the time, because the fourfold covers, where the branch is just a simple transposition, I like to say they're a lot less. They're more loosely knit, and it's a lot easier. Almost every one I ever looked at has a nice constructible ciphered surface to bound one of the branches.
You always
Lou,
work
you
with
look
three
puzzled.
color. You always work with three colorings, yeah?
Well, yeah, no, I've done dihedral
I mean,
coloring.
in this collection,
in this particular collection, these are the three colored examples with nice bounding surfaces in the covers.
Mm-hmm.
And I don't know of any others. It's about half of all the examples. But once again, you have to have an integral linking number for this to work, and then you have to have just the right diagram. But it doesn't seem to work for knots as simple as 7-4 or 7-7. Although it seems to me, if you raise the crossing number enough, it will work. And if you look at Schubert's normal form for 7-4 or 7-7, which is a kind of a nightmare because it's got a huge number of crossings, there is an easy way to see a surface that bounds the index 1 branch. And I use that to prove a theorem about how those linking numbers have to be related. It turns out an irregular dihedral cover has one branch of index 1 and then a whole bunch of branches of index 2, but all of the linking numbers between any two branches are determined by the linking number of the index 1 branch with the others. So there's a nice matrix that tells you don't have to calculate them all. In those days, I think Capel and Shanison were also working against the Poincaré conjecture, and they had some invariant that they wanted to show, and that particular formula for dihedral covers simplified their formula for calculating that invariant. You got any more pictures to show, Lou?
I have another set of slides of yours if you want to try them.
Yeah, show something. I can talk about it if I have time.
Wait a minute. There you go.
Yeah.
That's this.
Yes. Seifert and Trelfall gave a really nice chapter on covering spaces and enumerated all the 3- and 4-sheet covers of the trefoil knot. So I wrote up a little thing that added the double cover for the trefoil knot. I can't seem to scroll this thing, Lou. Can you scroll it up a little?
Yeah, just tell me to scroll.
Yeah. So these are the 6 different branch covering spaces of the trefoil knot through 4 coverings, 4 sheets. And the top 3 are cyclic. The bottom right one is locally cyclic, which means there's just one branch curve. But the other 2 have multiple branch curves, which means you can calculate the linking numbers. And I say, this is a little paper that shows how to calculate them. Sometimes just by looking at pictures. I go on to say I rely on the time-honored techniques of legal argument. Oh, I love that language. You skipped over it, Lou. I just love that language. The time-honored
sorry.
the bottom. We rely on the time-honored techniques of legal argument. Yeah, finger pointing and arm waving. Anyway, if you scroll to the next page, this shows again how you go from a one-dimensional covering to the Riemann surface to the thing on the right is what Hagar did in his thesis. And then I think you pointed out, Lou, that the bottom part of that page sort of gives a breakdown on how the 2 cells get related based on whether you've got a tricolored crossing or a monocolored crossing. And it's very hard to keep track of this, but I found it easy to just leave it alone. Just let it sit on the page as a diagram with segments marked and 3 colors, and you can carry in your mind what that picture results in and how. Can you scroll, Lou?
There's more. Just tell me when you want it scrolled.
Yeah, scroll to the next page. This page just talks about how you give everything a name and you set up equations and everything, but then scroll to the next page. Here. But that's the general algorithm that I gave in my thesis on how you can give everything a name and do a whole bunch of linear algebra and calculate the linking number. But you can also just jump right in and look around for it. This is that's the old trefoil, but this is the trefoil mapped onto, I guess, A4, where these are the permutations, the ways of matching the stuff underneath. And here you get 2 branch curves, one of index 1 and one of index 3. And the 4 things on the right show how to construct a little Seifert style surface that bounds 2 times the index 3 branch. And it's intersected 3 times by the other branch, therefore the linking number is 3 divided by 2. And it's nice that you can see that. I think if you keep scrolling on this one, Lou. Yeah,
get into another paper.
Yeah, this paper has appeared. The referee wouldn't buy the title, so it's appeared under a more modest title, but it's word for word the same paper. If you scroll to the next page. Oh no, I guess it's the next 3 here. The bottom of this page shows the 5-fold covering of, I guess it's the what do you call that? The 4 knot, right?
Figure 8.
And that's the figure 8. And that shows it's how you glue together along the 2 cells to construct its dihedral covering, its irregular dihedral covering. And if you scroll a little bit more to pick up the top of the next page, this shows how from this picture there are 3 different branch curves, one of index 1 and 2 different ones of index 2. But from this is a particularly user-friendly diagram of the covering space, because you can bound either one of the two different index 2 curves. You can bound this one by lifting to copies 5, 3, and 1. And if you look at how what that does, it bounds one of the curves, or you can lift it to 3 different copies in this way to co-bound the other curve. And then this is just the other thing that goes right through it. All right, scroll a little bit more, Lou. Scroll. This is a 2016 paper in Journal of the knot theory and its ramifications, which is kind of a pun if you're discussing covering spaces. Scroll away. Berman, when they invented the Jones polynomial, Berman found these 2 lovely knots that had the same Jones polynomial, but could be proven different by calculating the linking number in their 4-fold covers. And this is just an exercise on how to do that. And if you can scroll more, Lou. Oh, and here I came back then to the Perko pair, which is pretty hard for a lot of people to see. So I did a 21st century version that basically it's just 2 little flips. You keep the black part of the knot fixed, and you flip the other 2 parts around, and that changes the rive. And the rive is still a great mystery. It's definitely an invariant or a set of invariants for the minimal crossing diagram of any knot, but why there should be more than one for a minimal crossing diagram is, am I right to say, Lou, wholly unknown?
Pretty much.
Mhm.
And that's about all I have to say. And I would just go back to that first slide, Lou, which had the first one just had
This one or farther up? No,
way back. Yeah, before. One more before.
I'm sorry. I flipped into a different slideshow entirely. These are different. This one. There's this one.
No, the one that showed Hagar.
You mean the very first slide?
Very first one.
Yes.
Yeah.
Yes.
I mean, I think that pretty much says it all.
Yep.
And what it shows you, which nobody remarked at the time, but you can take Haggard's 3-fold covering of the trefoil knot, lift it up to look at the linking number in the covering, and you also get a handy dandy proof that it's not amphichiral.
Yep.
Because the linking number is +2, not 0. So if you orient 3 space the other way and you take the mirror image, you get a different knot. Now I don't think this stuff is too hard to teach beginners. I mean, it's just looking at the pictures. But you're the teachers. What do you all think?
I think so.
Yeah. But I do think, though, that you would need to perhaps go in a bit more on what a 2-fold covering, branch covering really is. I mean, you'd have to explain that first, or an n-fold.
Yeah, I don't know how to explain it other than by that top picture in the middle, which is the way Browner explained Haggard's thesis. But Haggard, this is, by the way, is a very good paper by Stilwell that I cite here, the AMS Bulletin, which was a beautiful forum for explaining this to a lot of people. And he talks about these two first illustrations are from that, and he talks about it very nicely. And he points out that Haggard had two different ways of seeing three manifolds, and it turns out this covers every three manifold. It's either a threefold covering of some knot like this, or it's one of these Haggard splitting diagrams where what do you do? You take inner tubes or something and sew them together differently. And Stillwell remarks that the Haggard diagram stuff is taken off like crazy, and all kinds of people have worked with that. Not many people have worked with the simple threefold covering space. And the fact that, I mean, they teach three coloring to kids, and the fact that every three coloring gives you a covering space and a link in the covering space and a linking number that you can often see. I mean, that's one hell of an invariant without investing almost any mathematics. So really, Haggard really proved everything all the way up through Dane, proving that the two trefoils are different.
I think it's remarkable that this was done over 100 years ago.
Well, the remarkable thing is Reidemeister took it off in the direction of algebraic symbols, and that kind of got everybody a lot more confused than you have to be.
Yeah, that's true.
But
anyway,
the Seifert
thought...
Threlfall book is very geometric. Did they discuss the irregular coverings in their book?
Yes, that's that other throw that long thing on again. The one that starts out with
Lehrbuch der Topologie by Seifert and Threlfall.
Yeah. Lou, you have that the third one.
There is an English translation.
Oh, you wanted another slide?
Yeah, just the one you had before with the first. Yeah, right. That's it. That page. The six. Those are the six coverings.
Oh yeah, I see. That's right. You did.
Seifert and Threlfall list them all. They don't draw any pictures, which is kind of sad, but they don't mention the double cover, but they mention the others. And these are all the covering spaces through four sheets.
They also studied cyclic branch coverings a lot.
Yes, yeah, and cyclic branch coverings were the Alexander and Briest method, and that worked very nicely for classifying knots through 8 crossings. But then it didn't work for the 9 crossing ones, which is why Reidemeister went into the non-cyclic coverings and finished up that work. Because cyclic coverings they give you the Alexander polynomial, and that's a pretty highly filtered invariant. I mean, a lot of knots it doesn't tell you much about.
Right.
And I never saw the benefit or the joy of going through all that algebra to get an Alexander polynomial that didn't distinguish a lot of knots. Well, it did. It distinguished a lot, but not. Well, I have all this stuff on my math blog, which I'm hoping somebody will pick up and run with it, because I only scratch the surface of what I can see, but you can do an awful lot more with these than anybody's done.
Lou, is it possible to
send us a? Sorry.
So I was just saying, is it possible to have copies of this on your website?
I think this is on my website.
No, I was thinking of Lou's website.
These will go into our Dropbox, of course.
Okay, excellent. Right. Okay. Yeah.
And you have a URL for your blog, Ken?
I just use ResearchGate.
I see what you mean. Yeah, sure.
I have 20 different
We can
things
always
on,
see what you have on ResearchGate.
I have 20 different. I've got more than you ever want to read.
Do you want to use the slides anymore, or shall we go back?
No, I'm done. I'm done.
Okay, there we go. So we're in conversation mode now.
But I love ResearchGate. I love to follow who's reading it and where. This week I've gotten reads in Russia, the U.S., Nepal, Ethiopia, Italy, the United Kingdom, and China. But I like the idea that there are not theorists in Nepal and Ethiopia. Do any of you know any of these people?
No?
Oh.
Oh, Nepal, maybe. There's a high school student who I talked with last year who went on to college, who's very keen on knots. It might be him who's reading it.
Could be.
His name is Avinash. I forgot his last name.
And Ethiopia, and then I was amused that one week somebody was reading my blog in the Fiji Islands.
Mm-hmm.
So a few weeks back, I showed a method of constructing braidings of threefold branch covers, which is based on work with Seiichi Kamada. And
You braid the covers? What do you do?
Yeah, I can put them in 5-space, either immersed or embedded, and they're braided, and they're sitting there quite explicitly. And I'd like to see this linking form there, as well as a talk you gave in Knots in Washington suggested that the way we were computing the linking form resembled how we compute the Jones polynomial. I mean, you do certain smoothings, and I think that's a good potential for understanding the geometric meaning of the Jones polynomial.
That's not something I've ever had any opinion on, so I'm not sure I suggested that. I think you're just suggestible.
No, you didn't suggest it. I just was looking at what you were drawing, and I said that looks an awful lot like smoothing crossings. So we should.
Yeah, Lou, you were looking for a way to get geometry from the Jones polynomial, weren't you?
Well,
we
don't have a good combinatorial description of the Jones polynomial except in terms of flat diagrams. So it would be good to know one.
Well, if there's one in 5 dimensions, I expect Scott Carter will find it.
Why not?
5 dimensions are too many for me. But Haggard's intuition was incredible because he didn't start working on knots with knots. He started working on functions of 2 complex variables. And it turns out that the trefoil is x to the y minus x squared minus y to the z. And if you map that as just as on real 6-space, you get a nice drawing of the complex function x to the x squared minus y to the 3rd, and he projected that down to 3-space, to an immersion on 3-space, which produced all these branch coverings.
Yeah, that's right.
That people still have a hard time understanding. And he's the guy that counted on his fingers, Haggard.
Well, I think we ought to give Ken a good clap for this interesting talk.
Many people believe I deserve a good clap, but of a different sort.
Well, we won't comment any further.
Thanks to Roger for being here on his birthday.
Oh yeah, well, it's part of my joy of birthday. I've already had the liquid lunch, so that's.
We won't ask how old you are.
Oh, don't! It's frightening. Anyway,
Well, it's better than the alternative. That's my only excuse for getting old.
that's right. Yeah. Yeah. It's the cure you don't want. Okay. Well, that was great.
Thank you again, guys.
No, it's our
Thank
pleasure.
you.
Thank you. Thank you.
Now, Tuesday, Lou, are you going to talk?
Tuesday, I'm talking. Yep.
Yeah. Okay. Great. So we'll look forward to seeing you all on Tuesday.
What's
Do we-
happening next
do we-
Friday?
What happens on Friday, right?
Oh, well, if nobody else is wanting to give a talk, I'll give a talk.
Great.
But I'm still trying. What about Lorenzo? When are you going to talk?
2 weeks.
Oh, 2-finger job.
No. 2 weeks from today, if that's
2 weeks.
okay.
Yeah, sure. Okay. Yeah, that will work out nicely. Okay. What about Brian? When's Brian going to give a talk?
Oh, think about it, maybe.
Okay. Right. So is that a definite maybe?
No, it's a maybe.
Oh, hello,
maybe.
Sergey. You look different. You still in Ohio?
Yes, I'm still in Ohio.
Yeah.
I guess I am the same.
Brian, is your
Sure,
connection working well enough to talk now?
Sorry?
Not now. Now I'm teaching. Actually, I have intensive teaching, summer teaching. Maybe
Sergey
later.
wrote a book where he described actually the original numbering system for 11 crossing knots as old Perko's notation.
You know, I'm also not young now.
Yeah, well. Okay, so I'll end this this talk now, and maybe Lou and Sam, maybe a quick discussion later.
Enjoy the rest of your birthday, Roger.
I certainly will. Yeah,
More
I
liquid.
think a single malt scotch, I think, by the telly.
That's it.
I need a 5-minute break and I'll be with you.
Okay, fair enough. Yep.
Okay.
Thanks again, guys.
Thank you.
Bye-bye.
Thank you, Ken.
Thank you,
Great
Ken.
talk. Thank you.
Bye-bye.
Thank you. Yeah.
Bye.
Bye now.